Hi students, this is our kinetic theory of gases lesson. Here in our JEE Neet coaching, there are some assumptions of kinetic theory that we have to consider while deriving the expressions as well as formulas, or even to solve some problems. We need to remember these assumptions. The first one is a gas consists of very large number of molecules. These molecules are identical, perfectly elastic and hard spheres. Please note down these points while watching the video clip itself. So gas consists of large number of molecules and these are always in a spherical shape and they are elastic nature. Elastic means when they collide with this one, so they will go back to their original position and they may oscillate about their main position, but the shape will never changes because of the elastic nature. The second one, the actual volume of the gas is negligible as compared with the volume of the container. If you take the container in which a gas is filled, let us say the volume of the container is 1 meter cube, but while solving the problems we will consider the volume of the gas in this container as 1 meter cube only. So, if you compress all these gas molecules, we can compress this gas into a small volume, and this volume may be 0.00000000001 meter cube. So, we can compress the entire gas into a small volume also. But we should not consider this volume. While solving the problems, we have to consider the volume of the gas is equal to volume of the container only. The third one, molecules do not have any preferred direction motion. Motion is always random motion. So we studied this in PUC also. So this is in this direction, this molecule may move in this direction, this molecule may move in this direction, this molecule may come down, this molecule may go up, this molecule may move in this direction, this may go like this. That means different molecules at a given time will have different direction of motions. So, in general, for a rigid body, all the molecules will move in a straight line, or all the molecules will move in the same path or in the same direction. But gas molecules will have different directions at different times, and that's why it is called a random motion. These molecules travel along straight line and motion free path for the same time. The time of collision is very small between the two molecules. The first one, between two collisions, suppose if you take one gas molecule here, one more gas molecule here, and it is moving towards this one, always moves along a straight line. But after that, this time of collision is very small. So, in mechanics, while taking a body of mass m1 moving with a velocity u1, collide with a particle m2 moving with a velocity u2, there the rate of change of momentum is equal to force, or the impulse is given by change in momentum. So this is the time of collision. So we can calculate this one, we will get some value, and this value also very small. But here this time of collision is very small. And next point, all the collisions are elastic in nature. So this collision is not inelastic or perfectly inelastic. That means two gas molecules never combine together. That means they cannot combine together and they cannot move with the same velocity. But that happens only in case of perfectly inelastic collision. So now in that perfectly inelastic collision, two molecules, two bodies may stick together and move with the common velocity. So this common velocity is not at all possible in case of these gas molecules. If it moves with the velocity u1, after collision it moves back with the velocity u1 only. This velocity generally never changes. That's why collision is said to be elastic, and due to this kinetic energy never changes. Kinetic energy with which it is striking the other molecule is 10 joules. The kinetic energy with which it comes back in the opposite direction is also 10 joules only. As 10 joules energy is a scalar, so it remains same. That's why Ke is conserved for this gas molecule. Next one, the motion of molecules is governed by Newton's laws of motion. So we can apply Newton's laws of motion here. So this is Newton's laws of motion only. So even if you want to find out the force, we can multiply mass of the gas molecule and acceleration of the gas molecule. We can apply this these Newton's laws for this gas molecule. Next one, the effect of gravity is negligible. While finding the equation of force, generally in case of pulley, suppose if you take this is the body of mass m1, this is the body of mass m2, and this is tension and this weight is m2g. So for writing this one, m2g minus t is equal to m2a. So here we consider the weight of this body, not only the tension, but in case of gas molecule, as the masses of the gas molecules are very small, the weight of the gas molecule is negligible. So in any derivation in this kinetic theory of gases, we are not going to consider the mg value, that is effect of gravity, that means weight of the particle should not be considered. Then the last one, the average of the path travelled by a molecule between two collisions is called a mean free path. So what is this mean free path? Let us say this is one gas molecule colliding with the wall of the container and coming back. So between these two collisions, it is moving along a straight line. So that's already we discussed in this point. So if you take this distance, this is not the mean free path. Mean free path is, this is the first collision, this is the second collision, this is the third collision, this is the fourth collision, this is the fifth collision, this is the sixth collision. If you take all these distances, take the average of all these distances, that the average of the distances travelled by the gas molecule between two collisions is called a mean free path. Is pressure of an ideal gas. So how to find out the pressure of an ideal gas? Generally we studied in fluids, pressure is equal to force acting per unit area. Suppose if you take a container here, if these are the gas molecules, so what is the area of this one? Area means total force by total area. If you want to find out pressure at a particular point, then area is this one. This is the normal force exerted by this gas molecule on this one. And the area vector is also taken perpendicular to this surface. So this is area vector. Generally what we can write? Force vector by area vector. So the area vector is always perpendicular to the surface that we are considering here. Suppose here if you want to find out the pressure, you draw a normal to this surface. This is called area vector. Here this is area vector. Here this is area vector. Here this is area vector. So area vector is radially outwards for a spherical surface. So A bar is normally outwards for a spherical body, for a spherical surface. Suppose if you take a gas in a container, so this container is filled with a gas. So what are the area vectors for this one? The area vectors are given by this side. For this surface, this is the area vector. 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 And at the bottom also it is given. And for this one, this is the area vector. So area vector always perpendicular to the surface that we are considering here. So let us say for this one, for this, what is the area vector? This area vector is always perpendicular to the surface. So angle between these two is always 90. Now, here, while finding the pressure, we need to divide the force acting per unit area, and this area vector is generally normal to the surface that we are considering here. But here, this is the pressure of a ideal gas. So what is an ideal gas? A gas which obeys all the gas laws at all temperature and pressures is called ideal gas. Now, let me take one ideal gas in a container. So here, this is our container. So in this container, I am going to take one ideal gas. So this consists of so many number of molecules, gas molecules, all are spherical balls. Let us say n molecules are there. Capital N is the number of gas molecules, and m is the mass of each molecule, mass of each gas molecule. Now, what is the total mass of this one? Number of gas molecule into mass of each molecule. So that I am going to write n is equal to m into mass of each molecule into n. So this is the total mass of the gas in this container. Total mass of the gas in this container. Now here I am going to derive the pressure of this ideal gas in a container. Here let L be the side of the cube, that is container. So this length I am taking it as L. So if you consider a molecule which is present here and it is moving towards this wall, and after collision with the wall, let us say it is coming back in the opposite direction with the same velocity. Why? Because already we discussed that the collision is always elastic. Generally, if a molecule collides with another molecule, pressure will not be created here. Pressure will be created whenever this molecule collides with the wall. Here, the collision between two molecules will result only the change in direction of velocity. Or if the velocity of the molecule is slightly different, as the masses are same, they will just exchange their velocities. So velocities will be exchanged or direction of velocity will change. But how the pressure can be created inside a container? So this is purely due to collision with the walls. Collision of gas molecules with the walls of the container. So there already we discussed N is the number of molecules, small m is the mass of each molecule, and capital M is the total mass of the gas in this container. Now, first let me take one particle here. This is the particle under study. So it is moving from here to here. Let the path of the path traveled here is L. Now, mass of this molecule, each particle is m. So this is m. Let us say it is traveling with a velocity v1. But v1 can be resolved into three components when this particle is moving in a particular direction. Let us say this is v1, and this can be resolved into vx1, vy1 as well as vz1. So this v1 velocity of this particle can be resolved into three components. So let me take this velocity which is moving, which is along this path and striking that wall and coming back. So in our case, this is the phase with which this molecule is going to collide. So let me take it as A, B, C, D. This is E, F, G, H, like this. Now, what is the momentum of this particle? Momentum of gas molecule before collision. Momentum is nothing but mass into velocity. I am considering only the velocity along x-axis. So this is m into vx1 because I am taking the first particle. So this velocity is vx1. So after collision, as it is elastic collision, the velocity direction will change, but the magnitude of velocity never changes. Momentum of gas molecule after collision is given by minus of m into vx1. So what is the change in momentum? Of gas molecule is given by the final momentum minus initial momentum minus mvx1 minus mvx1, which is given by minus 2m vx1. So this is the change in momentum. But what is the time taken for this gas molecule to collide again with that one? So let us say it collide with this one, coming back and colliding this one. So what is the total distance traveled between two collisions? Distance traveled is, this is L and then L. Total distance traveled is 2L. And what is the velocity here? Velocity Vx1. Speed you can write Vx1 only without bar. So here you can write Vx bar, Vx bar, Vx bar, Vx bar. If you want to take only the magnitude, so this is magnitude of change in momentum is given by 2m Vx1. That is twice of the mass of the velocity of the particle in mod. Mod means I am not considering this minus, I am not considering the vector. I am taking only the speed. Now, what is the time between two collisions with wall? Between two collisions, first when it collides with this one, it is coming back a distance L, and then once again it colliding with this one. So to collide with this wall, it is traveling 2L distance, and speed is Vx, not Vx bar, Vx. So we can write, we know velocity is equal to distance by time, and time is equal to distance by velocity. Now we know the magnitude of change in momentum, and we know the time. So from Newton's second law, the rate of change of momentum of this particle, rate of change of momentum of this particle is given by, this is change in momentum, that is delta P. So this is change in momentum delta P, and this is a delta T, very small time. So dP by dt, so I am going to write this as 2mvx1 by 2L by vx1, 2 get cancelled, m vx1 square by L. This is the rate of change in momentum of this particle. As we studied this, the rate of change of momentum is nothing but the force experienced by that body. Here the force exerted on this wall is given by, so F is equal to dP by dt, which we got it as mvx1 square by L. So this is the force exerted by this single particle on the wall. But every time so many particles are colliding with this wall, so that's why we have to consider not only a single particle, let us say n particles are colliding with this one. So for this is for one particle, for one molecule I can write, one gas molecule. For n gas molecules, because this container consists of n molecules, so for n gas molecules, this is given by, the net force is given by n gas molecules, F net is equal to force due to first particle, force due to second particle, force due to third particle, and so on, force due to nth particle. So what is the force due to one particle? This one. So I am going to write this as m vx1 square by L, m vx2 square by L, m vx3 square by L, and so on, m vxn square by L. For n molecules, we can write this equation as F net is given by, you can take m by L common, this will become m vx1 square plus m vx2 square plus, and so on, m vxn square to m by L into, so this is vx1 square plus vx2 square plus so on, so n into vx square. This can be written as m into n by L vx square. But m is mass of each particle, n is total number of gas molecules, and this will become the total mass of the gas in this container by length of this container into vx square. So this is only the average square of the velocity of the gas molecule along x-axis. But the molecule will never favor a particular direction. So it may move along x-axis, y-axis, z-axis. So from this word what we can write, v square is equal to vx square plus vy square plus vz square, or v is equal to square root of this one. This is how we can find the velocity of a particular gas molecule, this one. So v1 is equal to vx1 square plus vy1 square plus vz1 square. Now we know that the velocities are same in all directions. We can write vx is equal to vy is equal to vz. So this can be written as v square is equal to 3vx square, or vx square can be written as v square by 3. Now in place of vx square I am going to write the total mass by total length into v square by 3. So this is the net force experienced by this one. Now as we are going to find out the pressure of an ideal gas, the pressure is given by force by area. We know the net force, which is given by m by L V square by 3. And what is the area? All these molecules are colliding that surface, and the area of this one is, this is length and this is L length. So area of this one is L into L, L square. So I'm going to write this as L square. So this is M by L square goes up L cube 3 V square. This V is the root mean square velocity of the gas molecules. What is this L cube? This is the volume of that container. In the assumptions, we assumed that the total gas volume of the gas is equal to volume of the container. So we can write this pressure as mass by 3 times the volume of VRMS. What is mass by volume? This we write as the density. So pressure is equal to 1/3 rho VRMS square. So this is the pressure of the gas, which is given by 1/3 rho VRMS square. Ideal gas equal to 1/3 rho VRMS square. So this is called root mean square velocity of the gas molecules. How to find root mean square velocities? Before that, first let me write this as P into 3. This is 3P is equal rho VRMS square. So what is VRMS square? This is equal to 3 times the pressure of the gas by density of gas. So the VRMS speed of root mean square velocity of the gas molecule is given by root over 3P by rho. Now, based on this one, suppose if the pressure of the gas increases, what happens to the root mean square velocity of the gas molecule? Generally, students think that whenever this value increases as these two are directly proportional to each other. But if the temperature is constant, it is found that P by rho always constant. If pressure doubles, rho also doubles. If pressure is halved, rho also halved. This ratio never changes. Root mean square velocity never depends upon the pressure of a gas if its temperature is kept constant. If temperature changes, yes, then the pressure and density will change and the root mean square value will change. But what is the relation between VRMS value and temperature? So I am going to write this as, here we know that from ideal gas equation PV is equal to nRT. In place of P, V, this is mass by gram molecular weight into RT. So P is equal to M by V, M naught RT. This mass by volume is density. So now P is equal to rho RT by M naught. So P by rho is equal to RT by M naught. So the same expression, the root mean square velocity of gas molecules can also be written as root over 3 into, what is this P by rho, which is equal to RT by M naught. Very, very important for PUC as well as competitive exams. So generally, whenever temperature increases, what happens to the root mean square velocity of the gas molecules? Always increases. If temperature is doubled, what happens to VRMS? So one problem, VRMS 1 by VRMS 2 is equal root over T1 by T2. Why? Because 3 is a constant. Molecular weight of a gas is always constant. R is a universal gas constant which is equal to 8.31 for joule per mole per Kelvin. So it only depends on temperature. I am writing this one. If temperature is doubled, Tt cancel, this will become 1 by root 2. The new root mean square velocity equal to root 2 times the VRMS. This is how you can find the relation between root mean square velocity and temperature. Pressure of an ideal gas is given by P is equal to 1/3 rho VRMS square. Now, if you multiply this with 2, divide with 2, you will get a pressure equal to 1 by 3. This density is equal to total mass by total volume of the gas, VRMS square 2 by 2. You can see this one. The kinetic energy of the gas molecules is given by this is half mv square. This value is half mv square. So the kinetic energy of any body is equal to mv square by 2, that is half mv square. Now this you can write, pressure is equal to 1/3 V into this value kinetic energy of the entire gas into this we have 2. So PV is equal 1/3 of KE into 2 or 2/3 KE. So this is a 2/3 of KE. So what is the kinetic energy of a gas in a container? So we want kinetic energy, you bring this one this side. So this will become 3/2 times the product of pressure and volume. Now, we know that from ideal gas, PV can also be written as nRT. So kinetic energy of the gas is equal to 3/2 times of nRT. Here it is clear that the kinetic energy of the gas is directly proportional to 3/2 constant, n constant, r constant only depends on temperature. That means whenever the temperature increases, we can say that the kinetic energy of the gas has increased. That means temperature only depends upon the kinetic energy of the gas, but not the other energies like potential energy. Here, that's why the name of this lesson is kinetic theory of gases. Gases temperature increases due to increase in temperature. So it is clear that whenever temperature increases, kinetic energy increases, or in other terms, whenever kinetic energy increases, the temperature of the gas also increases. So in this case, if you take the total energy of a gas, it is the sum of KE plus PE. But why we are not considering this potential energy? In those assumptions, the gas molecules are at large distance from each other, and as the distance is too large, the potential energy generally given by product of the masses by distance into G, that is capital G m1 m2 by r. This is the potential energy between two gas molecules separated by distance r and having masses m1 m2. But as we said, the effect of gravity is negligible. So that means this potential energy is negligible. So we will not consider potential energy. So first one, gravitational potential energy between two gas molecules is 0. Second one, potential energy also develops between these molecules whenever there is an interaction between the molecules. But in this assumptions by this Maxwell, here Rydberg, here there is no interaction energy between any two gas molecule. So as there is no interaction, suppose if you take two mass particles having some mass, there is gravitational interaction between these two. Due to this, they will always try to attract with each other. Similarly, if you take a positive charge and negative charge, they will try to interact with each other. And if you take both similar charges also, they will try to repel with each other. This is also interaction only. But that type of interaction is absent in case of the gas molecule. That's why whenever there is no interaction energy, the potential energy will become 0. That means for a gas, the total energy is nothing but the kinetic energy only. Here, the total kinetic energy or nothing but the total energy of the gas is due to the rise in temperature. So that means whenever this total energy increases, the temperature of the gas will increase. So how to increase the temperature of the gas? By increasing their kinetic energies. That's why this is named as kinetic theory of gases. Real gas, that is P is equal to 1/3 rho Vrms square. Here, by using this, we can derive the gas laws here. First of all, if temperature is constant for this gas, now I am going to write this P is equal to 1/3 rho Vrms square. We know that Vrms is equal to root over 3RT by m naught. Let me substitute that value here. The pressure is given by 1/3 rho Vrms is equal to root over 3RT by m naught. Vrms square will become 3RT by m naught. 3 get cancelled. Pressure is equal to total mass of the gas by total volume into RT by m naught. Remember, this is total mass of the gas, this is molecular weight, both are not same. Now, this can be written as PV is equal mRT by m naught. So as I assumed that the temperature of the gas is constant, what we can write, the right side term will become PV is equal, what are the constants on right side? Mass of the given gas is always constant. This is a universal gas constant. As we assume the temperature is constant, T will be constant, and molecular weight of a given mass is always constant. So all the terms on right side are constant. So PV is equal to K. That means product of pressure and volume of a gas is constant. So from this we can write P is equal to K by V. Pressure inversely proportional to volume if temperature is constant. So this we call it as Boyle's law. If temperature is constant, because already I wrote here, if temperature constant. So this we call it as Boyle's law. So we derived this Boyle's law from the pressure of an ideal gas. So from this we can say the pressure of an ideal gas inversely proportional to its volume at a constant temperature. The second one, if P is constant at a constant pressure, so let me write this as P is equal to 1/3 total mass by total volume into Vrms square will become 3RT by m. So this is 3RT by m naught. Now you bring the volume and temperature this side, V will come here, temperature will go down. The other terms are mass of the gas 3R by 3 m naught P. Here 3 get cancelled. V by T is equal. What are the terms on right side? M, R, m naught and P. As I said, the P is constant here. This pressure is constant. So this is constant. This is constant. Universal gas constant. Mass constant. So this will become K, that is constant. So V by T is constant. V directly proportional to T, or V1 by V2 is equal T1 by T2. So this we call it as a Charles law. So what is the statement of Charles law? At a constant pressure, the volume of a given mass of the gas is directly proportional to the temperature. You might have studied this in chemistry, but statement I will write later. And the third one, if the volume is constant, if the volume of the gas is constant, so how you can write this expression? We know that P is equal to 1/3 rho V square rho. What is Vrms square? 3RT by m naught under root. Vrms square means 3RT by m naught. 3 and 3 get cancelled. Pressure is equal to rho RT by m naught. So let me write this rho as mass by volume. Now as volume is constant, keep volume that side, bring all the terms this side. P by T is equal mR by V m naught. So what are the constants here? Mass of the gas once again constant, universal gas constant, volume is constant according to our assumption, and this is a molecular weight. So all are constants. So finally we can write P by T is also constant, which is equal to, I can take it as K, and this is called P by T means we can write P1 by T1 is equal P2 by T2. So this we call it as a Gay-Lussac law. So what is the statement for Gay-Lussac law? At constant volume, the pressure of a given mass of gas is directly proportional to its absolute temperature. Remember, in this derivation, I am not considering the temperature in Celsius or Fahrenheit scale. And each and every time, whenever temperature is there, I am taking this as a absolute temperature. Now, let me write the statement for Boyle's law. Here, Boyle's law. Here the pressure inversely proportional to the volume. The pressure of a given mass of gas is inversely proportional to volume at constant temperature. So this is Boyle's law. Now if I want to draw a graph for this Boyle's law, so let me take this as PV graph. So this is P, this is V. We know that whenever pressure increases, volume will decrease. Pressure increases, volume decreases, but the product remains same. So the corresponding graph is always a rectangular hyperbola. So you will get a graph like this. So this is a rectangular hyperbola. So please remember, whenever two physical quantities are inversely proportional to each other, the corresponding graph is always a rectangular hyperbola. Similarly, if you take this Charles law, so what is the statement for Charles law? Charles law states that at constant pressure, the volume of a given mass of gas is directly proportional to its absolute temperature. Here I am going to write the Charles law. At constant pressure, the volume of a given mass of gas is directly proportional to absolute temperature. So now, if you want to draw the graph for volume and temperature as pressure is kept constant, for directly proportional, the graph must be a straight line and the corresponding graph will be like this. This is pressure and temperature. We studied this in the thermal properties of matter also. The volume of the gas always becomes zero at 0 kelvins. So these are the different temperatures that are given here. So this is a straight line passing through origin. If you take the absolute temperature along x-axis and volume of the gas along y-axis. Similarly for Gay-Lussac law also you will get the same diagram, same graph. Here pressure will come, and then the statement also just replace pressure with volume and volume with pressure. So what is Gay-Lussac law? At a constant volume, the pressure of a given mass of a gas is directly proportional to its absolute temperature, and corresponding graph, this is VT graph, and this PT graph is also a straight line passing through origin. So what is the meaning of this one? The pressure of any ideal gas will become zero at 0 kelvins.